It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our journey so far, we've explored the mechanics of search, how an AI can navigate a complex problem space to find a solution. But finding a path through a maze is one thing. Understanding what a maze is, what walls are, and what it means to be trapped, that's a different challenge entirely. It's the challenge of knowledge. Imagine walking into the great library of Alexandria, but with a terrible twist. All the scrolls, all the accumulated knowledge of the ancient world have been unspooled and thrown into one enormous chaotic pile. The information is all there, but it's useless. It's just noise. This, in a nutshell, is the problem that raw data presents to an artificial intelligence. Data without structure, without organization, is not knowledge. Today, we're going under the hood to explore one of the most fundamental pillars of artificial intelligence, a field that forms the very backbone of countless AI applications, from medical diagnosis to the search engine in your pocket. We are talking about knowledge representation and reasoning, often abbreviated as KRR. This is the art and science of building the card catalog for an AI's brain. It's the process of taking the multifaceted, messy, and often ambiguous complexities of the real world and translating them into a formal, structured format that a computer can understand, manipulate, and most importantly, reason with. Let's define our terms. Knowledge representation, or KR, is the process of encoding information. It's about systematically capturing the essential components of our world, the entities within it, like people, places, and objects, their attributes, like color, size, and age, and the intricate web of relationships that connect them all. Reasoning, on the other hand, is the cognitive process of using that represented knowledge. It's the decision-making mechanism within an intelligent system. If knowledge representation builds the library, reasoning is the act of walking through the aisles, pulling different scrolls, comparing them, and drawing a new conclusion that wasn't explicitly written anywhere before. Crucially, these two concepts are locked in a symbiotic dance. They are two sides of the same coin. The quality of your knowledge representation dramatically impacts the effectiveness of your reasoning. A poorly organized library makes for a frustrated scholar. Conversely, the act of reasoning, of testing the knowledge, of pushing its boundaries, helps to validate and refine the representation itself. They are mutually enhancing components of any intelligent system. So here is our roadmap for today. We're going to start our journey in the optimistic dawn of AI, exploring the philosophical dream of capturing all of human thought in simple, elegant symbols. We'll build up from the ground floor, learning the basic alphabet and grammar of machine reasoning, propositional logic. Then we'll see how AI learned to move beyond simple rules, to draw intricate mind maps of the world using semantic networks. From there, we'll explore the powerful engines that allow an AI to perform logical inference, to connect the dots. We'll pay a visit to a pioneering digital doctor from the 1970s, a system called Mycin, and we'll see how its conceptual DNA lives on in the massive globe-spanning brain that answers your search queries today. By the end of this episode, you won't just know that an AI can know things. You'll understand the very architecture of that knowledge, the blueprints that engineers use to build intelligence, one fact, one rule, and one relationship at a time. To understand knowledge representation, we have to travel back to the very birth of artificial intelligence as a field. In the 1950s and 60s, a powerful and seductive idea took hold, an approach that would dominate AI research for decades. Today, we often call it symbolic AI, or, with a mix of reverence and nostalgia, good old-fashioned AI, GOFAI for short. The central hypothesis of symbolic AI was this: intelligence, in all its glory, could be achieved through the mechanical manipulation of symbols according to a set of formal rules. This idea didn't come from nowhere. It was the natural extension of centuries of work in mathematics and philosophy. Thinkers like George Boole and Gottlob Frege had already laid the groundwork by demonstrating how logical reasoning could be treated as a form of calculation, a systematic process that could, in principle, be automated. This was the intellectual climate that gave rise to the first true AI programs. At the legendary Dartmouth workshop in 1956, where the very term artificial intelligence was coined, the pioneers of the field were filled with a profound optimism. They truly believed that a machine with human-level intelligence was just a matter of years, perhaps a couple of decades away. And this optimism fueled the creation of groundbreaking systems. In 1959, two projects emerged that set the stage for all of KRR to come. The first was John McCarthy's proposal for a system called the Advice Taker, a hypothetical program that could accept new knowledge in the form of simple declarative sentences and use it to reason about the world. At the same time, Alan Newell and Herbert A. Simon were developing the General Problem Solver, a program that aimed to mimic human problem-solving strategies by manipulating symbolic representations of a problem. These weren't just computer programs. They were attempts to formalize the very process of thought. To do this, they needed a language, a formal, unambiguous language to write down facts about the world, and they found it in the bedrock of mathematics, formal logic. The most fundamental building block for symbolic knowledge representation is a system called propositional logic, sometimes known as propositional calculus. If we're building a language for an AI to think in, propositional logic provides the alphabet and the most basic grammar. It's a system for representing simple, atomic facts about the world and the logical relationships between them. The core unit of propositional logic is the proposition. A proposition is simply a declarative statement that can be evaluated as being either true or false, but never both at the same time. It's a binary claim about the state of the world. For example, the sky is blue. This is a proposition. We can look outside and determine if it's true or false. In logic, we might represent this with a single symbol, like the letter P. It is raining. This is another proposition. Let's call it Q2 plus 2 equals 4. This is a proposition that is always true. Now, these individual facts are useful, but the real power comes when we connect them together. Propositional logic gives us a set of tools for this, called logical connectives. These are the grammar of our new language. Let's make this tangible with a running example. Imagine we're programming a simple smart home system using propositional logic. First, we have the AND connective. The AND operator says that the combined statement is true only if both of the individual propositions are true. Our smart home rule might be, turn on the air conditioner. This action depends on two facts. Let's say P is the thermostat reading is above 75 degrees, and Q is all windows are closed. The rule in our AIS knowledge base would be, if pages and Q is true, then activate the AC. If it's hot but a window is open, the condition is false. If the windows are closed but it's cool, the condition is false. Both must be true. Next is the OR connective. The OR operator says the combined statement is true if at least one of the individual propositions is true. Our rule could be, turn on the porch light. Let's say P is, the sun has set, and Q is, the motion sensor is triggered. Our rule is, if pages or Q is true, then turn on the light. The light will come on if it's dark or R if someone walks up the path or both. Then we have the simplest connective, Not. It does exactly what you'd expect. It inverts the truth value of a proposition. Our rule: do not run the sprinkler system. Let's say P is the rain sensor detects moisture. The rule is, if not P is true, then it is okay to run the sprinklers. If the sensor is wet, meaning P is true, then not P is false and the sprinklers stay off. Finally, and perhaps most importantly for building intelligent systems, we have the implies connective, represented by an arrow, which we read as implies. This is the foundation of if-then rules. The statement P implies Q reads, if P, then Q here. P is called the antecedent, and Q is the consequent. This one can be a little tricky. The implication P implies Q is only considered false in one specific scenario, when the antecedent P is true, but the consequent Q is false. In all other cases it's true. Let's use a classic example. If it is raining, which we'll call P, then the ground is wet, which we'll call Q. If it's raining, P is true and the ground is wet, Q is true, the rule holds. True. If it's not raining, P is false and the ground is dry, Q is false. The rule holds. True. If it's not raining, P is false, but the ground is wet for some other reason, like a sprinkler, Q is true. The rule still holds. The rule never claimed that rain was the only cause of wet ground. True. The only time the rule is broken, the only time the implication is false, is if it is raining, P is true, but the ground is somehow magically bone dry, Q is false. That's a contradiction of the rule. Using these simple building blocks, atomic propositions and logical connectives, early AI researchers could construct a knowledge base, a collection of facts and rules about a specific domain. For example, an early medical diagnosis system might encode facts like, patient has a fever, let's call it P, and patient has a cough. Let's call it C, then it could add a rule. If a patient has a fever and a cough, then they might have the flu, which we'll call F in propositional logic. That rule is written. P and C implies F. The system could then use this knowledge base to make logical deductions. But here, we arrive at a critical turning point in our story. For all its clean mathematical elegance, propositional logic has a profound and crippling limitation. Consider the most famous syllogism in the history of philosophy: all men are mortal. Socrates is a man, therefore Socrates is mortal. This is a perfectly valid argument. The conclusion is guaranteed if the premises are true, but try to represent this in propositional logic. You can't. You'd have to represent all men are mortal as a single proposition. Let's call it P. You'd represent Socrates is a man as another proposition. Q and Socrates is mortal would be a third. R. The argument becomes, given P and Q, therefore R, from the perspective of propositional logic. This is nonsense. There is no logical connection between P, Q, and R. They are just three distinct opaque statements. The problem is that propositional logic cannot look inside the propositions themselves. It has no way of understanding that Socrates is an individual entity, that man is a class or category to which he belongs, and that mortal is a property associated with that class. It can't handle concepts like all or some. It treats Socrates is a man with the same atomic granularity as the sky is blue. This failure was not a bug. It was a feature of the system's design for simplicity. But it revealed a fundamental truth that would drive the next several decades of research in knowledge representation. The history of this field is a story of constantly inventing new tools to solve the limitations of the previous ones. Propositional logic was powerful but not expressive enough. To build truly intelligent systems, AI needed a way to represent not just facts, but the rich, structured relationships between the objects that those facts describe. This quest for greater expressivity would lead researchers down a new, more intuitive path. This also highlights a fundamental tension that exists in the design of AI systems to this day: the trade-off between expressivity and tractability. Expressivity is the richness of the language, what it's capable of representing. Tractability is the computational cost of reasoning with that language. Propositional logic is highly tractable, it's computationally cheap to work with, but it's not very expressive. The next generation of tools would have to find a new balance, increasing the expressive power, often at the cost of making the reasoning process much more complex. So, to reason about Socrates, an AI needs more than just a list of true or false statements. It needs a model of the world. It needs a way to understand that things exist, that they belong to categories, and that they have complex, meaningful relationships with each other. The rigid, linear structure of formal logic was proving too brittle. Researchers needed something more flexible, more connected, more human. This led to the development of a new approach, one inspired not by mathematics, but by cognitive psychology and how the human mind seems to store information: semantic networks. If propositional logic is like writing sentences, a semantic network is like drawing a mind map. It's a graphical way to represent knowledge, consisting of just two simple components. Nodes, which are also called vertices, represent concepts, objects, or entities. Edges, which are also called arcs, represent the relationships between those nodes. This approach is incredibly intuitive because it mirrors the way we think, through association. When I say the word canary, your mind doesn't just retrieve a single fact, it activates a whole web of related concepts. Bird, yellow, sings, flies, pet. A semantic network aims to capture this web of meaning explicitly. Let's build a simple semantic network together, verbally, to represent some knowledge about a cat named Tom. First, we create our nodes. We'll need a node for the specific individual, Tom. We'll need nodes for the categories he belongs to, like cat, mammal, and animal. And we'll need nodes for properties or other related concepts, like fur and cream. Now, we connect them with labeled edges that define the relationships. We draw an edge from Tom to cat and label it Isa. This link signifies that Tom is an instance of the class cat. We draw an edge from cat to mammal and label it a kind of. This link signifies that cat is a subclass of the class mammal. Similarly, an a kind of edge connects mammal to animal. Now for properties. We can draw an edge from mammal to fur and label it haspart or simply has, and we can represent a behavior with an edge from cat to cream, labeled likes. What we've just described is a simple graph, a small constellation of interconnected ideas. This graphical approach is a natural fit for capturing complex, hierarchical relationships. And this hierarchical structure unlocks the superpower of semantic networks: inheritance. Inheritance is a form of inference. It's the idea that if an object belongs to a class, it automatically inherits the properties of that class, and of all the superclasses above it. Look at our network. We never explicitly stated that Tom has fur, but we can infer it. The reasoning process goes like this: Tom is a cat is a kind of mammal. A mammal has fur, therefore by inheritance Tom has fur. This is an incredibly powerful and efficient way to store knowledge. You don't need to specify that every single mammal has fur. You state it once at the mammal class level, and all subclasses, cats, dogs, bears, whales, automatically inherit that property. This reduces redundancy and makes the knowledge base much easier to maintain. Semantic networks were a huge leap forward. They were intuitive, flexible, and captured the associative nature of knowledge far better than logic alone. But they had a significant weakness, especially in the early days. The meaning of the nodes, and more importantly, the labels on the edges, were often informal and ill-defined. What does a likes relationship really mean? Does it mean all cats like cream? Most cats? Is it a preference or a biological necessity? In one system, an ISA link might mean is an instance of, while in another system down the hall, it might mean is a subclass of. This ambiguity made it difficult to share knowledge between different AI systems or to perform rigorous, guaranteed correct logical reasoning. The field needed more rigor. It needed a way to make the meaning of these networks formal and explicit. This need gave rise to the concept of an ontology. The word ontology comes from philosophy, where it means the study of being or existence. In computer science and AI, the definition is very specific. An ontology is a formal, explicit specification of a shared conceptualization. That's a mouthful, so let's break it down. Formal. This means it's machine-readable. The specification is grounded in well-understood logic, so a computer can process it without ambiguity. Explicit. This means that all the concepts, properties, relationships, and constraints are clearly and unambiguously defined. Nothing is left to interpretation. Shared. This is key. An ontology provides a common vocabulary and a conceptual framework for a particular domain, like medicine, finance, or automotive engineering. The goal is to create a consensus, an agreement on meaning, so that different people and different computer systems can communicate effectively. Conceptualization. This just means it's an abstract model of some phenomenon in the world, identifying the relevant concepts of that phenomenon. Think of an ontology as a supercharged, formalized version of a semantic network. It's not just a picture, it's a dictionary, a grammar, and a rulebook for a specific domain of knowledge, all rolled into one. This idea of creating shared, formal models of knowledge is the driving force behind one of the most ambitious projects in the history of the Internet, the semantic web. This vision, championed by the inventor of the World Wide Web himself, Sir Tim Berners-Lee, is of an extension to the current web. It's a vision where the information on web pages is given well-defined, machine-readable meaning, transforming the web from a collection of documents for humans to read into a vast, interconnected database that machines can understand and reason with. To make this vision a reality, the World Wide Web Consortium, or W3C, developed a stack of technologies. Two of the most important are RDF, the Resource Description Framework. This is a standard way to describe things on the web. It represents information in simple statements called triples, which consist of a subject, a predicate, and an object. For example, the subject is Mona Lisa. The predicate is was created by. The object is Leonardo da Vinci. This simple structure allows knowledge to be represented as a massive interconnected graph. OWL, the Web Ontology Language. OWL is a language built on top of RDF that allows you to write rich, complex ontologies. You can define classes, subclasses, properties, and logical constraints, like a person can only have one biological mother, or a square is a rectangle whose sides are all equal in length. It brings the full power of formal logic to the web of data. To help crystallize these ideas, let's verbally walk through a comparison of the techniques we've discussed. Think of this as a summary of their strengths and weaknesses. First, propositional logic. Its core idea is representing facts as atomic true-false statements linked by connectives. Its strength is that it's simple, computationally fast and efficient, what we call tractable. It's excellent for building straightforward rule-based systems. Its main weakness is a severe lack of expressivity. It cannot represent objects, their properties, or the relationships between them. Second, semantic networks. The core idea is a graph of nodes representing concepts and edges representing relationships. This model is highly intuitive and visual. It's excellent for representing hierarchies, and its structure naturally supports the powerful concept of inheritance. However, these networks are often informal. The meaning of the relationships can be ambiguous, and they lack a standardized, formal semantics. Third, ontologies. The core idea is a formal, explicit specification of the concepts and relationships within a domain. Ontologies are formal and unambiguous. They enable a shared understanding between systems, which is critical for interoperability, and they support rigorous logical reasoning. Their primary downside is complexity. Creating a robust ontology can be an incredibly difficult and time-consuming process, a problem known as the knowledge acquisition bottleneck. The evolution we see here, from simple logic to intuitive but messy networks to formal and standardized ontologies, is not just a technical progression. It reflects a profound maturation of the field of artificial intelligence. It's the story of moving from building small, isolated, toy systems in a laboratory to attempting to build a global, interconnected, and machine-understandable web of knowledge. The initial innovations were creative and idiosyncratic, but for this technology to scale and become a true foundation for global intelligence, it had to be standardized. Just as the Internet required standardized protocols like TCP/IP to function, a true web of knowledge required standardized representation languages like RDF and OWL. A knowledge base, no matter how elegantly structured as a logical system or a semantic web, is ultimately just a static collection of information. It's a library, waiting to be used. To bring this knowledge to life, to make it active and useful, we need a second component, an inference engine. The inference engine is the part of an AI system that interprets and evaluates the facts and rules in the knowledge base to solve problems and derive new information. It is the mechanism for reasoning. And while there are many ways an AI can reason, we're going to focus on two of the most fundamental modes of thought, deduction and induction. Deductive reasoning is what most people think of when they hear the word logic. It's a top-down process. It starts with general principles or rules that are assumed to be true and uses them to arrive at specific conclusions that are logically certain. The key phrase here is logically certain. In a valid deductive argument, if the premises are true, the conclusion must be true. There is no ambiguity. This was the primary mode of reasoning for the first wave of symbolic AI. The goal was to build systems that could reason with the rigor and certainty of a mathematician proving a theorem. The workhorse of deductive reasoning, the most fundamental rule of inference, is a principle with a Latin name, modus ponens. It's also known as affirming the antecedent. The structure is beautifully simple. Premise 1, if P, then Q, this is our general rule. Premise 2, P is true. This is our specific observed fact. Conclusion, therefore Q must be true. Let's revisit our old friend Socrates. Earlier, we saw that propositional logic couldn't handle this argument, but with a more expressive representation, like a semantic network or an ontology, modus ponens can do its work. Premise 1, our general rule, all men are mortal. We can rephrase this as an implication. For any entity X, if X is a man, then X is mortal. Premise 2, our specific fact, Socrates is a man. Conclusion. By applying modus ponens, the inference engine concludes, therefore, Socrates is mortal. This simple rule is the engine that drives expert systems. The AI chains these implications together. The conclusion of one rule becomes the premise for the next, allowing the system to reason its way from a set of initial facts to a final, complex conclusion, just as a detective follows a chain of clues. Now let's turn to the other side of the reasoning coin, Induction. If deduction is top-down, induction is bottom-up. It's the process of moving from specific observations or examples to broader generalizations or rules. Unlike the ironclad certainty of deduction, the conclusions of inductive reasoning are probabilistic. They are likely, but they are not guaranteed to be true. A classic example of induction is this: Observation 1. The first swan I ever saw was white. Observation 2. The second swan I saw was white. Observation 1000. The 1000th swan I saw was white. Conclusion. Therefore it is probable that all swans are white. For centuries, this was a perfectly good inductive conclusion. It was a strong generalization based on a large number of specific instances. Of course, it was ultimately proven false with the discovery of black swans in Australia. And this highlights both the incredible power and the inherent peril of inductive reasoning. It's how we form most of our beliefs about the world, but it's always open to revision by new evidence. Now, this is a crucial link to the rest of our series, because inductive reasoning is the philosophical heart of modern machine learning. The entire paradigm of symbolic AI was based on deduction. Human experts would painstakingly write down the general rules of the world, the knowledge base, and the AI would use deduction to apply those rules to specific facts. Machine learning flips this script completely. Instead of being given the rules, the AI is given a massive amount of data, the specific observations, and its task is to infer the general rules on its own. This represents a monumental shift in the philosophy of building intelligent machines, and it's a topic we will dedicate the next several episodes to exploring in depth. Before we move on, it's worth briefly mentioning a third type of reasoning: abductive reasoning. Abduction is often described as inference to the best explanation. It's the kind of reasoning that doctors and detectives use every day. You're given a set of observations or symptoms, and you have to infer the most likely cause. Observation. The ground is wet. Abductive conclusion. The most likely explanation is that it rained. It's not a deductive certainty. A sprinkler could have been on, but it's the most plausible hypothesis given the evidence. This distinction between deductive and inductive reasoning reveals something fascinating about the history of AI. In human culture, we tend to idolize deductive reasoning. We associate it with logic, rigor, mathematics, and pure intellect. It feels like a superior form of thought. This cultural bias heavily influenced the first generation of AI researchers. They set out to build machines that think like logicians, that operate with deductive certainty. But as some have pointed out, this may have been exactly the wrong approach. We think deduction is so impressive precisely because, as humans, we're actually quite bad at it. Our brains don't seem to be wired for formal logic. What our brains do, naturally and effortlessly, is induction. We are masterful pattern recognition machines. So, the early attempt to make a machine emulate human intelligence by programming it to be a master of deduction was, in a way, like trying to replicate the subtle dexterity of a human hand by building a powerful vice. The shift in modern AI towards inductive learning-based systems wasn't just a technical upgrade. It was a profound philosophical correction. It was a move toward building machines that learn in a way that is much more aligned with how biological intelligence seems to operate. We've covered a lot of theory. We've talked about logic, networks, ontologies, and engines of inference. Now, let's see how these ideas come together in the real world. We're going to look at two case studies, one from the classic era of symbolic AI and one that you interact with every single day. Our first stop is Stanford University in the early 1970s, at the birthplace of a landmark expert system called Myson. MYCIN's mission was ambitious: to act as a consultant for physicians, helping them diagnose severe bacterial infections like meningitis and recommend the correct course of antibiotic treatment. Let's look at its architecture. Mycin was the quintessential expert system. It had two distinct components: a knowledge base and an inference engine. The knowledge base, Mycin's brain, consisted of a collection of approximately 600 if-then production rules. These rules were not discovered by the machine. They were painstakingly extracted from human experts, leading infectious disease specialists. Through a long and arduous process of interviews, a typical rule in MYCIN's knowledge base looked something like this. Rule 52. If the site of the culture is blood, and the organism's Gram stain is negative, and the morphology of the organism is rod, then there is suggestive evidence with a certainty of 0.4 that the identity of the organism is Pseudomonas. The inference engine, MYCIN's reasoning engine, used a process called backward chaining. Instead of starting with the facts and reasoning forward, it would start with a possible hypothesis. For example, the hypothesis, the organism is Pseudomonas, and work backward, trying to find evidence in the patient's data that supported the if clauses of the relevant rules. Because medicine is rarely black and white, Mycin also used a system of certainty factors, numbers between 1 and +1, to represent the degree of belief in a piece of evidence or a conclusion, allowing it to weigh conflicting information and arrive at a probable diagnosis. How well did it work? Astonishingly well. In formal evaluations, Mycin's performance in recommending therapy was found to be on par with, or even slightly better than, human specialists in the field, and significantly better than general practitioners. It was a resounding success. It proved that the specialized, nuanced expertise of a human expert could be captured in a symbolic knowledge base and be reasoned with effectively by a machine. But here is the most important part of the story. Mycin was never used in clinical practice. Why would such a successful system be relegated to the history books? The reasons are a crucial lesson in the difference between a laboratory success and a real-world tool. The knowledge acquisition bottleneck. The process of manually extracting knowledge from experts and encoding it into rules was incredibly slow, difficult, and expensive. Experts often don't know how to articulate the tacit, intuitive knowledge they've built up over decades of practice. This bottleneck was a fundamental barrier to scaling up expert systems. Usability and integration. Mycin was a standalone system running on a large, time-shared mainframe computer. A doctor would have to leave their patient, go to a terminal, and manually type in the answers to a long series of questions. It wasn't integrated into the hospital's workflow or patient records. It was simply too cumbersome to use. Ethical and legal questions. And of course, there were the inevitable thorny questions. Who is legally responsible if the AI makes a mistake and a patient is harmed? The doctors, the hospital, the programmers at Stanford. These were questions society was not ready to answer. Mycin's true legacy, therefore, was not as a medical tool, but as a proof of concept. It demonstrated the power of the expert system paradigm and directly led to the development of expert system shells, like MYCIN, toolkits that provided the inference engine and user interface, allowing developers to build expert systems in other domains simply by plugging in a new knowledge base. Now, let's fast forward 4 decades. The dream of building a comprehensive knowledge base about the world never died. It just got bigger, a lot bigger. In 2012, Google announced a project that represents the modern, scaled-up, and automated realization of the semantic network dream, the Google Knowledge Graph. The mission of the knowledge graph was to fundamentally change how search works. The goal was to move beyond simply matching keywords in documents to actually understanding the things, the real-world entities that users were searching for, and the relationships between them. It was a shift, as Google put it, from strings to things. Let's look at its architecture, and the contrast with Myson is stark. The knowledge base. The knowledge graph is a single massive semantic network containing, as of 2020, over 500 billion facts about 5 billion entities. It stores information about people, places, organizations, creative works, scientific concepts, and so much more. Data sources. Here is the critical difference. Mycin's knowledge was handcrafted. The knowledge graph's knowledge is ingested automatically. Google's systems crawl the web and pull information from structured sources like Wikipedia, Wikidata, and the CIA World Factbook. They also license data for things like stock prices and weather forecasts. Crucially, they also use natural language processing to extract facts from the trillions of pages of unstructured text on the open web. The impact of this KRR system is something you experience every single day. When you search for Eiffel Tower, that box that appears on the right side of the results, the one with pictures, a map, the height, the architect, the opening date, that is the knowledge graph in action. It's called a knowledge panel. It's answering your factual question directly, without you needing to click on a single blue link. It's using its understanding of the Eiffel Tower as an entity and its relationships to other entities, like its location in Paris, or its architect Gustave Eiffel, to give you a synthesized summary of knowledge. The story of Mycin and the Google Knowledge Graph is the story of the evolution of knowledge representation itself. It perfectly illustrates the transition from knowledge engineering to knowledge ingestion. Mycin was a masterpiece of artisanal knowledge engineering, with every rule carefully handcrafted. The knowledge graph is a monument to industrial-scale knowledge ingestion, with its content largely populated by automated processes. This monumental shift was only made possible by two things that the researchers in the 1970s simply did not have. First, an unimaginably vast source of raw data to learn from, the World Wide Web, and second, the maturation of machine learning and natural language processing techniques powerful enough to read, understand, and extract structured knowledge from that messy, unstructured data. The fundamental challenge of KRR has shifted. It's less about finding the single perfect way to represent knowledge, and more about building powerful tools to populate those representations automatically from the ocean of data that now surrounds us. Today, we've journeyed through the very heart of classical AI. We started with the crisp, clean certainty of propositional logic, where the world is composed of simple true or false facts. We saw how the limitations of that simple model forced the field to embrace a more connected view of the world, leading to the intuitive mind maps of semantic networks and their rigorously formal cousins, ontologies. We then fired up the engines of inference, watching how machines can reason deductively like a logician and, in a sign of things to come, inductively like a scientist. Throughout this journey, we've seen a core engineering challenge surface again and again: the fundamental trade-off between expressiveness and tractability. On one hand, you want a representation language that is rich and expressive enough to capture the complex, nuanced, and often messy details of the real world. On the other hand, you need that representation to be computationally tractable, meaning you can actually reason with it in a reasonable amount of time without the problem spiraling into a combinatorial explosion. This balancing act remains one of the central challenges in designing intelligent systems. What we've really been talking about today are the two distinct souls of artificial intelligence. The first is the soul of symbolic AI, the world of knowledge representation and reasoning we've just explored. This approach is top-down. It is explicit, logical, and, importantly, interpretable. Knowledge is engineered by humans into clear rules and structures. Its greatest strength is its precision and its clarity. When a system like Myson makes a recommendation, it can show you the exact chain of rules it followed to get there. The second soul is that of machine learning, and particularly of neural networks. This approach is bottom-up. It is implicit, statistical, and often operates like a black box. Knowledge isn't engineered. It's learned from the patterns found in vast amounts of data. Its greatest strength is its incredible ability to handle the noisy, complex, high-dimensional data of the real world, images, sounds, and natural language, and its remarkable adaptability. For many years, these two approaches were seen as competing philosophies, with researchers firmly in one camp or the other. But today, one of the most exciting frontiers in AI research is the quest to bring them together. This field is called neural symbolic integration. The goal is to build hybrid systems that combine the strengths of both paradigms, to create AIs that have the powerful pattern recognition and learning abilities of neural networks, but can also reason about the world in a structured, logical, and explainable way, using the kinds of knowledge representations we've discussed today. The quest is to build an AI that can not only perceive the world, but truly comprehend it. We've spent this episode talking about how we can meticulously build knowledge into a machine, piece by piece. But what if a machine could construct its own knowledge simply by looking at examples? That is the revolutionary promise of machine learning. Next time on AI Deconstructed, we leave the world of handcrafted rules and formal logic behind. We step into the world of algorithms that learn from data as we begin our multi-part deep dive into the foundations of modern AI, machine learning.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.